Hello and happy reInvent, everyone. Today we're going to talk about what monitoring means to us at Amazon and some stories about how we've applied it and proved it at Amazon over the years. This covers a bunch of practical things that we've learned within Amazon that should potentially apply to how you monitor your own systems as well. I'll be using some specific examples that you make use of Amazon CloudWatch because that's commonly what we use at Amazon, but these tips should apply to things that whatever monitoring system you use also. We'll start with some of our overall monitoring philosophy to give some context, and then we'll get into some specifics and interesting challenges that we've found when it comes to monitoring things that are noisy and when our metrics lie to us. I like to think of monitoring about a way to view the running system. Actually, less of a way to view the running system, and more about a way to view the customer experience. So sure, we monitor things about the system like CPU and memory, but when we talk about latency and availability, that's actually more about a lens with which to view the customer experience and empathize with what customers are seeing. And at Amazon, as we as software developers operate the systems that we build. So for this talk, I'll bring in examples from the systems that I've built and then operated at Amazon over the years, like AWS Lambda currently, DynamoDB, IoT, and actually even back to the Amazon.com web server fleet. So let's start there to introduce monitoring philosophy. So I'll go back to the team that I worked on Amazon.com. We operated the Amazon.com web server fleet. So we ran this HTML rendering fleet that kind of pieced together all the HTML for the website and sent it back to browsers. And so this ran code from developers around Amazon who were responsible for the various widgets on the site. And in order to provide a personalized experience for each of those widgets and each page of the site was very dynamic and made a bunch of service calls for rendering each page. To get data about each product, each reviews, shopping cart contents, and that sort of thing. This picture shows Amazon.com, the call graph or the service-oriented architecture a couple of decades ago. This isn't all about Amazon.com. This was also back-end systems, but you can get the idea of all the data dependency and the service-oriented architecture dependency. And you can imagine the web server fleet is kind of in the middle there. So one interesting story is about how we measured latency. So imagine we're measuring the latency, server-side performance across various types of pages. So the latency to render the search results page, for example. Now, if we look at the product page, where we show the details of a single product, like its description, its images, price, product reviews, similar products that people shopped for, these are really long pages with a lot of features. And we had this kind of tension as a business. We wanted to keep innovating and adding more features to this and changing the features, experimenting with the best customer experience possible for shopping. But we also knew that people wanted a snappy, fast, responsive shopping experience with low latency. So we knew that both were important. And we had this tension as a customer for the customer experience to keep maintaining or improving latency while still innovating and adding features. But fortunately, we found a way to give customer the best of both worlds. We found that when we dug into the metrics, that what customers cared about the most was the latency above the fold. So above the fold in a newspaper, it means when you fold a newspaper in half, it's the part that you see kind of on a newsstand that kind of tells you what it's really the newspaper is going to be about and is trying to kind of convince you that you should buy that newspaper or that you might be interested in what's inside and give you a summary of what's going on in the day's news. So you can still flip through the back of the page, but above the fold latency, similar to a newspaper on the Amazon.com website, is what we found that customers were actually the most sensitive to. And so for Amazon.com, we needed to measure the above the fold latency the most closely. So we could take our time rendering the longer parts of the page because people would spend their initial time on the top of the page before they'd scroll down. So they'd still care about the overall page latency, but they weren't as sensitive. So this example illustrates how Amazon does a few different things when it comes to monitoring. Well, we introspected and we thought about which latency measurement mattered the most to customers. If we had only looked at whole page latency, we could have actually made a mistake. We could have improved the overall page latency while making the above the fold latency worse. And so we would have congratulated ourselves thinking that we made things better for customers when actually we would have made it worse for customers. We also measure from a lot of places. It's not just about server-side metrics. So for this feature, for measuring above the fold latency, for example, we had to instrument the client with JavaScript, callback, AJAX stuff. However, the meta point here is that we have to continuously look at our metrics and think about whether or not we're measuring the right thing. At AWS, teams get together every week and examine our key dashboards together. So we make sure that we understand how things are doing and if the metrics look good, but we also spend time, the bulk of that time, questioning to make sure that we're looking at the right things. So culturally, that's how we monitor and kind of why. But we have an overall monitoring architecture that's built around supporting that culture. So the ability to observe a system starts with instrumentation. We write code around the code that measures how long things take and how often things happen, what it's for, what the IP address, caller, whatever, metadata about requests. The thing is, we do that with a common set of instrumentation libraries that we try to standardize across Amazon. The reason for that is so that when we share code, that instrumentation code also interoperates. For example, if we have an application that's making a service call, we're using a client library that is instrumented using that same library. So we plug in application instrumentation into that client instrumentation, and it happens without having to write any glue code. The instrumentation is pretty simple, though. It just writes out logs. So the logs contain structured information about, how long things take, all those timers and everything. And we also have other types of logs that aren't less structured and contain just stack traces and that sort of thing. So these structured logs are the particularly interesting ones because these have all the performance monitor metric stuff. And it's kind of like the CloudWatch embedded metrics format that we launched last year. It was my favorite announcement of reInvent last year. It was a little more subtle one, but it's my favorite because it made it so easier for people to do things the way that Amazon does. So from there, these logs get pushed into archival systems in near real time, and so that we can use log analysis tooling to be able to ask questions about what's happening right now and what happened, kind of go back to the tape and look in the past to see what happened afterward. We can do flexible kind of ad hoc queries using log analysis tools. That's what they're designed for. These tools vary from downloading a log file and using literally grep, or using more sophisticated tools, which is more common, to use things like CloudWatch Log Insights, MapReduce type of approaches, or Elasticsearch. So those are the more common tools. Now, those logs, since they contain structured data about those measurements, our metric system, CloudWatch, just pulls those logs and produces metrics from them. And then so we take those key metrics and put them on dashboards that we look at often to diagnose what's going on. But since we aren't staring at the dashboards 24/7, we also have alarms that go off based on those metrics. And those will kind of alert operators to need to run runbooks, or for better automated systems to do things like automatically roll back in progress deployments and that sort of thing. Now, we also do tracing, which helps us understand the interactions between components in distributed systems. And so it's just another way of looking at and summarizing the system or drilling down into given requests compared to the other approaches. So it's very important that we found it's very important to keep that act of adding instrumentation as simple and easy as possible, because instrumentation is a key way that we improve the operation. So this is a flywheel. It turns clockwise. And as we add instrumentation, that produces these logs and metrics that we can see, which we look at and consume in the form of dashboards and alarms. And so as we look at those dashboards and we receive those alarms, that causes us to ask questions. And as we ask questions, in order to answer those questions, we need to add and change the instrumentation. Instrumentation isn't just something that we do when we develop a service. We're constantly adding it so that we improve the way that we operate and have better outcomes for customers. And so as we improve operations and kind of filter out the noise, this also lets us ask better quality questions and improve things further and keep that wheel spinning. So that's the high level. So now let's get into some specifics about how we deal with noisy metrics and make them clean. We'll talk about 3 different types of noise. So when I think about noise and noisy metrics or alarms, I think about the parable of the boy who cried wolf. So in this parable, there's this kid who's this farmer, and their job is when a wolf shows up, the kid is supposed to run to the village and gather the villagers who come and scare away the wolf. So that protects the sheep. So the problem is, this kid really likes the attention of everybody running in to come help the kid. And so the problem is, the kid gets bored one day. There's no wolf, but the kid gets bored and cries wolf and gets all the villagers to come in, but there's no wolf. So now the villagers have kind of lost trust. So come another day, when the wolf actually shows up, the kid runs and calls everybody, but they don't show up because they figure this kid is just vying for attention again. So the problem is, this made people distrust the alarm and ignore it even when it was a real problem. So clearly there's a bunch of cases when this alarm system is effective and somewhere where it's not. So let's kind of lay it out on a truth table. So on one axis, we have whether or not there's an alarm. And when there is an alarm, the farmer comes in, the villagers come in and save the day. And on the other axis, it's whether or not there's a problem. And so when there's a problem, there's a wolf. And so you can see this kind of these eventualities then, where see if there is no problem, there's no wolf, and there is no alarm, that's great. That's great. Things are just operating as usual. If there is a problem, there's a wolf, and there is an alarm, well, that's not great, but it's okay because the villagers are there to come deal with it. Now, if there is a problem but no alarm, that means no villager. That means the sheep is alone with the wolf, and that's not going to end well. But if there's no problem and there is an alarm, this is actually also a problem because this trains the villagers to ignore future alarms, and it makes the lower right quadrant more likely. Okay, so let's bring this back to metrics though. There are some metrics, you've probably seen graphs that look like this. There's some metrics that are noisy and hard to make sense of, and there are others that are clean, that have pretty nice signal. And noisy metrics are the worst two quadrants, and the clean metrics are the best two quadrants. Noisy metrics really can't be alarmed on the way we'd like because they're too painful and unactionable. So when we create alarms at Amazon, we want them to be actionable, like that action could be following a runbook or rolling back code, whatever. But when we're instrumenting code, we might not always know. We might be thinking, hey, I want to add a timer around this, but you don't know whether or not the result of that will be a noisy metric or a clean metric. So we might think, okay, well, if we find that it's noisy, let's just get rid of the instrumentation. But we find that's actually a mistake, because if there's something that seems like it's worth timing, there's probably something there, and we just need to use some techniques to make that a little more stable of a metric. And I'll get into those now. So let's start with an example. When we were building DynamoDB, we knew that customers would care about really low predictable latency for all different types of operations, writes, reads, and queries. So query latency is something we had to have really good monitoring of. So as we were developing DynamoDB and starting to operate it on test clusters, we were measuring the query latency and noticing that it was noisy. So that doesn't look predictable, but we had to dig into why. Well, it turns out a query can return either 0 kilobytes or up to 1 megabyte of data. And so both cases have predictable latency. They were just different when you're counting the microseconds. So our graphs were fluctuating, not because the system was misbehaving, but rather because the graph was dependent on customer behavior. If someone came along and started running a test with a bunch of large queries, it would make the metric do this, even though normal queries were performing just fine. So we had to solve this problem. We had to make it so spikes were actual spikes and not crying wolf. So the answer was actually pretty simple. But it followed that cycle culturally of what I was talking about earlier, where we kind of are constantly looking at metrics and refining our instrumentation. We just looked at the metrics with the team, as a team, and added an if statement. So we said, okay, take the small queries, the queries that end up not being very expensive, and report that duration as a separate named metric. And if the query is expensive, categorize that as a different metric. It's sort of a dimensionality that we had to incorporate into the instrumentation. And so that made it so that if these both cases were pretty stable metrics, like I was saying. And so if there was an increase, that would mean that there was actually something that needed investigation. Okay, so that's one type of noise. Let's talk about unpredictable traffic now when it comes to errors, specifically client errors. So what do I mean by that? Well, there are two types of errors generally in a web service. There are server errors, and those are pretty well understood. That means it was definitely the server's fault. There's some kind of error, timeout, whatever. But then there are client faults, and that's where the client didn't adhere to the API contract quite correctly. Maybe it didn't authenticate, maybe it sent a wrong parameter. So server errors, pretty easy to monitor. If there are any, it's a problem, essentially. So when things go up, that's a problem, and we need to automatically roll back or something if there's a deployment, or if it's stable, then it's fine. So pretty straightforward. Client errors are a mistake that customers made. So it's hard to say when we should actually alarm. But these errors shouldn't be ignored for two reasons. Well, for one, it helps us understand what our customers are going through. If customers are running into a particular invalid call path often, it's worth exploring that to kind of see why. Maybe they're running into a maximum description length often, and we could increase that and make their experience happier. Or we could talk to those customers who are running into some size maximum and find out maybe that they actually would prefer a different kind of API rather than putting a bunch of stuff into a description. So it's hard to say. But that's user experience research. It doesn't really need an operator engaged instantly. So it turns out there's actually a second case where we'd want to alarm on client errors. And it can be real problems. It can represent real problems that would otherwise go undetected. And so, oh, yeah, that's the wolf. Every API, this isn't something that actually happened. I'm speaking in hypotheticals here. So I work on Lambda, and we have this API called CreateFunction. And CreateFunction takes a bunch of different parameters, including the name of the function. And there's a limit. There are some constraints. You can only pass a function name that's so large. So what would happen? It's technically possible to write a bug. We have a ton of testing and different types of measures that would prevent this from going to production. But let's say, for the sake of argument, it happened where we had previously allowed 140 character function names, but let's say we started to only allow 100 character function names. Well, now there would be a lot of people who were already using large function names who would be broken by this. And the problem is this would be undetected, because if we say that we don't want to alarm on client faults, well, there's no server fault in this case. This would look to the server like a client fault. So we'd end up with a wolf without an alarm. So what do we do about this? Well, one kind of the problem is it's hard to set a threshold on the client error volume. One way to deal with this is CloudWatch has a feature that lets you put prediction bands on a metric. So it's useful for if there's a volume that you don't really know what volume the metric will be at. This just puts prediction bands on based on past metric observations, and that can work. We don't tend to use that technique here in this case because client errors are pretty unpredictable. What would happen if one client showed up and deployed a bug to their application and it caused the client errors to spike? Well, it would still be a spike and it would still alarm even if we were using this prediction band. A better way to do this is actually by looking at the per customer error rates. I know this is really hard to do when you have just an enormous number of clients, but there's a different way that's actually supported by CloudWatch called CloudWatch Contributor Insights. And it lets you measure the top N customers, like top 10, top 100 customers error rates or whatever, some other metric that you define. And so this is great. This shows that if we were to go and look at the Contributor Insights dashboard, we'd see this. We'd see that, oh, actually that was just one customer spiking. We should probably talk to them, but this isn't a server-side problem right now, probably. Now, if we were to see this pattern in that same thing, that would be a problem. That would say, hey, we might have pushed that code change that I showed earlier, and we just changed it for a lot of people. That's a problem. And so we would have to roll back automatically. Now, this graph, though, doesn't give you something you can alarm on. This is just something to look at. When you're looking at the top 10, you can't really set an alarm on that. Well, fortunately, with metric math, there is a way. This is just about, if we have this dimensionality where it's counting things per client, we can actually do some interesting metric math on different types of dimensions. So the way to do this, say with CloudWatch, is with Contributor Insights. Not only does it count the top 10, or top 100 matching of the certain dimension, it also approximates the total number of clients matching that filter. So what you can do with that then is say how many clients are experiencing any client errors in this minute and divide that by the number of clients total in that minute. So you get the number of clients experiencing any faults, client faults at all, divided by the total number of clients, and then you get the percent of clients experiencing any client errors. And that's a pretty stable metric. It's never zero because there are always customers kicking the tires, trying different things, and they're going to make an invalid request from time to time. But it stays pretty low and stable. And then if it goes up, that means there's some correlated, it's unlikely there would be a correlated workload of many clients all starting to experience errors at the same time. So it's a pretty stable metric. And it's stable, it means it alarms when it's a problem, and it doesn't alarm when it's not a problem. So now let's talk about a different type of noise in distributed systems, which is just inherent to the distributed system. So if we have, let's take a distributed system like AWS Lambda. This is a slide from a talk last year about how Lambda works under the hood. The specifics of what's going on here is not important. It's just components talking to each other, microservice architecture. But how do we make sense of this operationally? Because there's a lot going on. Like, how do you see which system we need to investigate or something? Well, for one thing is we make a lot of dashboards. We write these by hand. We curate metrics that are important carefully. So for each component, we make a dashboard, actually multiple dashboards, that show the health of different parts of that system, the interactions with other systems, and that sort of thing. But my system, we also then make roll-up dashboards that shows the overall kind of summary statistics. But this is there's a lot of metrics even just on this slide to sift through. So there are other ways, though, that we do this to make it a little bit simpler. And we do that with distributed tracing. The idea is this. When a request comes in at the entry point, we stamp that request with a unique request ID or trace ID. And as different systems interact with each other for that request, they pass along that trace ID like a baton in a relay race. It's important that they do that for each request. It takes code to do that, but they do. And as each component logs, it also logs with that trace ID. So we could, for example, take all the logs for a given time period and search for that trace ID and just gather them all up, and we have some nice timing information. But the next thing we can do is, if we're using a tracing system like AWS X-Ray, is those systems all send those per trace timings and everything to that central system, and then it can produce these types of graphs that show how long things took and where requests succeeded or failed. The other advantage of having that kind of central system is that it can summarize. Instead of looking at just one request as it flowed through the system, we can filter out the noise of that system, of all the complexity, and zoom in on aggregate metrics that show, okay, this is the component that we should be looking at right now that has questionable performance, and the rest of them are looking fine. So distributed tracing systems can help summarize things in a sort of a causal way that just raw metrics don't necessarily let you do. So those are some stories about separating signal from noise. And we do a lot of that at Amazon, but we found that there are some cases where metrics can just mislead us. So let's look at a couple of those cases. One of them, when it comes to measuring performance, we find that summary statistics, it's pretty easy to be misled by summary statistics, especially averages. So this graph shows, might be representative of the customer experience. You might think, oh, this is pretty great. But when in reality, there could actually be something going on there that we're just not seeing. So summary statistics are just very one-dimensional, right, because it's over time. But so we can actually get a little bit more information out of them by looking at a histogram instead. So to create a histogram, we take the latency, we take all the data points in a given time bucket, like all the data points over 5 minutes, and we put them into buckets according to how long the request took. So for example, the bucket of 15 to 20 milliseconds might have had 971 requests in it. And so by looking at a histogram like this, we can see that there actually might be some surprising distributions in there that we weren't expecting. We thought an average might mean that they're all kind of about the same, when in reality there could be modes. For example, we may find, oh, actually, the latency is a lot better when you have a cache hit and far worse when you have a cache miss. And so this could show that there might be customers who are more often landing in one of these two buckets, and this kind of helps us dig in by looking at a histogram. Now, histograms are super useful and visually tell quite the story, but they're a little harder to measure over time. So we found that it's useful to measure percentiles. So we look at a lot of percentiles, like the 99th percentile, for example, shows that the 99th fastest request out of 100 was this fast or slow. And we don't just look at one percentile. We make sure that our dashboards contain many different percentiles because information gets lost. This is a lossy encoding of a histogram. And it's just important to be mindful of that and eventually, and from time to time, look at an actual histogram. So that's where summary statistics can mislead, but there can be other times when the instrumentation code can be misleading and surprising. So here's a latency graph. Normally, this looks great, right? Well, we should celebrate. Our latency suddenly improved, abruptly, out of the blue, with no deployment. Well, but it could actually be that the latency improved because the errors spiked. And so this would happen if the instrumentation were measuring the overall latency and not separating out if the successful requests from the error requests. Maybe because oftentimes errors are much faster to serve than successful requests. From time that it varies, but it can happen. And so what we do to avoid this confusion is just to separate out, much like how we bucketed the small and the large queries in DynamoDB. We can bucket the successful responses time from the error responses time. And now we get something that's nice, and when it spikes, we know it's a problem. So another case where metrics can lie is going back to when I was working on AWS IoT. So we had customers who would have devices out in the field that would report metrics in every once in a while, like say every 5 minutes. And so we were working with one customer who had an analytics app who had an architecture like this: devices out in the field reporting every 5 minutes. Their analytics app they were building took in all those data, all the data points, and were producing metrics and driving their business. So the problem is they reached out to us because they were having trouble with their application getting overloaded periodically. And they thought, well, the actual amount of volume that's coming in is actually low. If our request can handle this, dotted line, then we shouldn't be getting overloaded because we can handle it. We aren't approaching our limits from their system standpoint. Well, we dug in, and what was actually happening is that the devices were just kind of sitting around, and then at the top of 5 minutes, they would all check in and report in their data. It would overload the analytics app, and then 1 second later, back to sitting around for the next 4 minutes, 59 seconds. And so this is a case where the metrics, the summary metrics, were actually lying. And because they were showing a different summary, they were actually showing something different than how we were interpreting them. We were assuming that was sounded the peak traffic, but that was actually just the average traffic over 1 minute. And so to actually prove this and to analyze and dig deeper, we looked at logs using kind of CloudWatch logs insights, and we can see that if we bin things differently than we prepared to with the metrics, again, it's important to have this ad hoc capability we find to be able to just ask questions that weren't there, even go back to the tape and go into the past. And since we have the raw data points, we can ask questions that we didn't think of ahead of time. And so if we bin things, we can find that actually they were seeing essentially 1 second or a couple seconds of every 5 minutes getting a big request spike. So this helped understand, and then you can add jitter and that sort of thing to make the traffic a little bit more friendly to their backend system. So while in this talk, I went in a bunch of details about things, and essentially all it boils down to are kind of 2 key takeaways. 2 things that we think about at Amazon that you might find useful to think about for your own systems as well. So first, monitoring gives us a powerful tool for understanding the customer experience. But getting those metrics right and getting monitoring right requires us to be curious about the metrics and ask questions as a team regularly so that we can tweak our instrumentation to measure what's really important and improve things further. And then second, some of the things that we need to measure in the customer experience are just inherently noisy. And so for those, we have various techniques like tiering, dealing with different dimensionality, aggregation, deduplication, whatever. But it's easy to be misled by metrics. So we use percentiles to tell a story that a single summary statistic can't. And we make sure to measure and combine measurements from multiple places in the distributed system and be able to kind of hop between those different ways of measuring and different ways of analyzing the metrics. Now, a lot of this stuff that I was talking about is pretty surface stuff. One other note is that at Amazon, when we're trying to dig into a more complex topic, we prefer to write about that instead, because this gives the writer more chance to kind of make sure they flesh out all the nuance and details and express that, kind of keep them honest. And it gives the reader more time to consume all of those details and think and reflect on it. So we've published, about a year ago, we published the Amazon Builders Library, and there are a few articles in there related to this talk that you might like, listed here. So if you want to dig deeper on those topics, check out the Amazon Builders Library. So thank you all for coming, and feel free to reach out to me on Twitter. We can talk about this talk or anything else. Thank you.